Thank you so much for coming to our second session. The second session of the conference will focus on outlining the current state of the field of cosmology and touching on the biggest problems, open and unsolved. It will provide a broad overview of the inference methods in the field. And finally, our speakers will also raise the important questions of how we can apply these methods effectively and efficiently as well. With that being said, I would like to invite just to sort of show you our first speaker, Ben Wandelt, who is joining us online with a pre-recorded talk. Thank you so much. So yeah, we can start the pre-recorded talk.
Hi, everyone. I wish I could be there with you, but unfortunately the logistics just didn't work out. And so thank you to the organizers for allowing me to present in this format. I'll speak about decoding the universe with ML inference, following on in this session from the previous two talks. Before I get started, I just want to flash this slide showing that there are many contributors to the results that I'll be showing. Many of them have been obtained in the context of the Simon's collaboration on learning the universe. So a lot of credit goes to the people involved. I want to highlight specifically also Matt Ho, who's been really key in pulling many of these strands together. All right, I know that there are a bunch of people around that are not necessarily cosmologists, so let me just give you a sense for why these methods are particularly useful for cosmology. Just to give you a sense of the range of scales and the type of data that we're working with here, I thought I'd show you the Planck data, cosmic microwave background data, and then how it relates to galaxy surveys. So we start with this all-sky data set looking at the very early universe and going all the way to a scale where, this is actually our Milky Way and we're looking at really just the local environment. As you can see, in the galaxy surveys, there are these filamentary structures that we understand now as emergent features from nonlinear interactions that occur on small scales. Here you see a simulation of that. A cosmic web emerges from this gravitational clustering with halos and filaments and voids. And in the very small scale regime, even more complexity is needed to capture all the physics that happen. So galaxy formation involves radiative transport, plasma physics, cosmic rays, chemistry, gas dynamics, star formation of black holes, and the interaction of all of those components. And so very quickly this becomes computationally extremely heavy. So how do we build in all these models, and what does this mean in terms of the overall subject? So really physical cosmology is taking these very early initial fluctuations shown here in a 3D view that we see in the cosmic microwave background, and then using all the physics we know and these cosmological parameters that I'm showing here that describe the recipe of the universe, the particle content, to predict observations. So these parameters also are sensitive to these mysterious components of dark energy, dark matter, and other parameters describe the statistics of the primordial fluctuations related to cosmogenesis. And what we actually want to do is then take these observations and infer all of these ingredients. So that's the part of cosmological inference. Now, to do that, obviously we need data, and cosmology is very richly equipped with data sets. I'm showing a small selection here. This is not complete, but contains some classic missions that have already been completed, observations and surveys, some that are currently ongoing, and some that are about to start operations. together, this is an unprecedented amount of data. And in fact, data in cosmology has been growing exponentially over decades now in essentially multiple subfields. So taking all these things together, the physical modeling, the availability of data, there's a huge opportunity because there's a third component, which is the breakthrough in the last, let's say, 5 to 7 years on being able to use the data and confront it with these detailed numerical models in a way that just wasn't possible before. For example, we can use machine learning to find automatically highly informative summary statistics for the data. We can solve computational statistics problems using trained models. For example, compute Bayesian posteriors. For example, even sample high-dimensional distributions. And all of these set of techniques, likelihood ratio estimation, likelihood-free inference, density estimation, those I summarize under the topic of implicit inference, or the label of implicit inference. I'll talk a bit more about that in a minute. We are even able to do model comparison, computing Bayes factors for purely computational models where we don't know how to write down the likelihoods. So this is really new, and I'm giving you a bunch of references here to look at the literature. Now, with these implicit inference techniques, will we get tighter constraints from the data? Will we just be able to squeeze out more information? Likely yes. Will we get better constraints on the data? Definitely yes, because having this ability of computational modeling, a lot more modeling flexibility, I think ultimately will lead us to better understanding and a better detailed analysis of the data. Actually implementing all of these techniques is can be a challenge, but we're actually trying to make it as easy as possible. So there's this LTU ILI pipeline that under the leadership of Matt Ho, we've been making available. You can download it. It gives you access to a bunch of different techniques and also builds in best practices like validation techniques to make sure that you don't misinterpret the results. The best part of it is you can write a full inference pipeline in just 5 lines of Python code using these techniques. So please feel free to check this out either on the archive or on GitHub. So with these techniques, are we done? No. It turns out we have multiple challenges, and I think the main challenges are, one, scaling the models to the size of current datasets and coming datasets, increasing the model fidelity to get out even more information from the data, and then ways to mitigate the approximations inherent in our models, in any model, of the complex physical reality that we observe in the sky. To illustrate that, let me show you a classic data set. It's no longer really state-of-the-art, but even that data set presents a great deal of challenges. So this is the Sloan CMAS sample, 2 parts of it. The smaller part is the South Galactic Cap, and the larger one, the North Galactic Cap. We are sitting there where the 2 arrows originate, looking out. And I'm drawing in a 1 gigaparsec cubed box, which is about the size of simulation that we can run thousands and thousands of times, even 10,000 times. But really, brute force simulations don't really scale much beyond that. And in any case, it's only the gravitational dynamics that are modeled by these simulations. If you put in all of the hydro stuff, it gets much, much harder. So we have a big scaling problem because no one has actually been able to analyze even the smaller part of this data set fully with these techniques. There's this larger North Galactic Cap, which has only been analyzed with traditional techniques, and current data sets are another order of magnitude larger. So we have developed these massively accelerated techniques for generating galaxy surveys simulating galaxy surveys, with the idea being that with these techniques that I described, as long as we can simulate it, we can analyze it. So CHARM is led by Shivam Pandey, postdoc here at Johns Hopkins, which is a generative model that produces fine-scale structure halos in the context of physically simulated 3D matter distributions. This technique is highly accurate. In fact, the points here are what you would get from running a full simulation, and the lines are the results that you get with CHARM. And so there you can see that really reproduce a number of standard kind of diagnostics, the power spectrum, the bispectrum, and even wavelet scattering transform coefficients, which were very good at picking out differences in texture. Here, I'm shown here on the lower right. If you use these fast simulations or fast emulations at the level of the field level data, so really individual halos, populating them with galaxies, we can show that, in fact, that allows us to train networks that are then good at analyzing the brute force simulations. So we get unbiased and well-calibrated posteriors. This is all part of our validation pipeline that we're building out to actually do the analysis on real data. So we can generate these galaxy catalogs with CHARM. This is one that actually you can see that. So on the right is the actual observed data. On the left, the simulated. Looks pretty similar for these parameters. For these parameters, you can see some differences. The clustering really is visibly off if you stare at this for a long time. So we have the ability to do this at scale now. And this is only the beginning. I mean, these are still based on so-called halo occupation distribution models, quite approximate, but there's a sequence of better approximations, more and more sophisticated approximations. And as long as we can emulate those, then we should be in business. And the idea is to run small-scale simulations and then learn from those and then scale them up to much larger volumes. So our current best front runner for these techniques is called Gotham. It is a transformer model that we have trained to essentially tell us, in terms of tokens, really tell us where halos or objects sit within a simulated environment. So we produce a 3D environment, and then it tells us here, there's a halo here, it has these properties and so forth. And we've also been experimenting with doing the same thing with galaxies and their properties that have been extracted from hydro simulations. So we're really learning to generate point sets and their properties, for example, galaxies, conditioned on environment. This, of course, has many other interesting applications outside of astrophysics, but we're excited about the potential here. This is very accurate and has been successful to much smaller length scales, deeper into the nonlinear regime. But I don't want to spend much more time on this. I want to get to another challenge, which is model misspecification. So, and ideas for mitigating that. This is going to be central because however sophisticated our model, will always be in a regime where the data, the real universe has more physics on smaller scales that we're not really completely including. And so how do we mitigate that? Well, one idea is to think of the universe as some code that we don't have access to. We only have access to the result. But then we can take the codes that we do have access to and try to guard against exactly the same effect. So we can, for example, train on multiple codes in such a way that the extraction of information becomes agnostic to which code actually ran the simulation. And so if we do that, we get these kinds of results. So these are embeddings of the simulation results. The first one is just if we train on these two different input simulations, you see the embeddings are separable. You can tell which simulation code they came from. But then when we switch on this forgetting factor, this agnostic factor, the simulations kind of get mixed. And as we expected, if we do cosmological parameter inference, so the top row does not have this forgetting factor switched on, this kind of adversarial factor penalizing for the ability to tell which simulation code was used. You see we get quite large parameter biases, and that gets significantly better if we include this factor. One issue I've kind of alluded to but not really gotten into is, well, how many simulations do we actually need? So we were looking at this with Anirban Baraji, PhD student in Paris, where we took a very simple problem statement where we say, okay, so if we trained a neural network to use the power spectrum of the dark matter to infer parameters, how many simulations do we need to train that neural network? And we use a publicly available set of simulations to do that. So we have techniques in this case from asymptotic statistics that tell us how much information there is. And here's how much information the power spectrum has on two key parameters, the sigma 8 and omega matter parameters that we're very interested in cosmology. So this actually gives us a gold standard. And if we train our network on sort of the standard number that a lot of people use, 2,000 simulations, we do not reach this information content. So we are not able to reproduce that. So 2,000 simulations are suboptimal. And this was not for lack of trying. Anirban spent a lot of time trying all kinds of different architectures and so forth. So the idea here is that by using this Cramer-Rao bound based on asymptotic statistics, we can and the scaling of how much information we get as we train on more and more simulations. Here's the asymptotic regime suggested by the Cramer-Rao bound. We can sort of extrapolate and say and estimate how many simulations we need to get into this asymptotic regime. Of course, we never get better than that. There will be an asymptotic approach, but trying to hit here will get us into the asymptotic regime. So it turns out, well, from doing this, it turns out we need about 4,000 or so, as you could see on the previous plot, and then if we actually compute the information content of these neural network summaries, we find that they do saturate, and we validate it with another run. In fact, this is also publicly available. It's called the BSQ, the Big Sobol Sequence run, that was run specifically to support this study that includes over 30,000 n-body simulations, which I think is the largest set of n-body simulations that has been run across different cosmological parameters. Then another scaling problem is, well, once you have a huge survey, how do you pipe it through your neural networks? And we can exploit the cosmological scale hierarchy by saying, let's use the neural networks on small scales where they're good at interpreting these complicated features. On large scales, we understand everything perturbatively, and we know the power spectrum and low-order endpoint functions must contain all of the information. So it turns out that by combining those, we should be able to really extract a lot of information. And this helps a lot because also splitting simulation volumes into smaller patches effectively gives more training data to the networks. We find that they train better with smaller number of simulations. And we're able to get the best constraints anyone has ever gotten at this level of resolution from these dark matter simulations in terms of information content, squeezing out information content. Here's another study together with led by Lucas Mäkinen, who showed that by training, again, neural summaries together with traditional summaries can actually work much better when you're in a simulation-limited regime. To finish, I just want to mention two things really quickly. We can go beyond just a handful or tens of parameters to actually full inverse problems. We've been doing that for quite a while, but mostly in the context of explicit likelihood, where we write down a likelihood and we have a code running, we do Markov chains. We've been able to reconstruct initial conditions and run them forward and generate these consistent histories of our universe that all produce the actual data shown in color here once you get to the present day. But we want to do this. That was done with approximate gravitational models. We want to do it with the full models. And so here's an example of using conditional diffusion models. This is work with Ronan Legin in a couple of years ago. Training on about 2,000 simulations, and then taking the output of the simulation, nonlinear output, and guessing the linear small initial seed perturbations that went into this. And this trains a conditional diffusion model, and as you can see, we can generate multiple realizations extremely fast in this business, or at the level of minutes per realization. These are very accurate reconstructions. They match the power spectrum of the true initial conditions, and they are highly cross-correlated with the actual true initial conditions used to run the simulation. Crucially, because of the way we set it up, differentiability is not required, so you can put any computational model in your forward pipeline and do this inversion. So that's something we're excited about expanding and developing for current data. And just to complete, I did want to mention this idea of being able to compare models. Model comparison for scientists is about the same as proving theorems for mathematicians. It's key to what we do, but computing these Bayes factors for model comparison has been a huge bottleneck. It's very, very challenging computationally and technically using traditional techniques. Even if you know what your likelihood and prior are exactly, it's difficult to extract this. You have to do this high dimensional integral depending on how many parameters you have. But in fact, rewriting this as a machine learning problem, it turns out it becomes independent of the number of parameters. That really doesn't figure in the final answer. And turns out that this here I'm comparing how long it takes to run the state-of-the-art sampling technique for evidence computations on a particular data set. And this isn't actually the runtime for our model. That would be much faster. It's the training time. So the training time is a couple of orders of magnitude better. And the error is smaller for this test. So I invite you to look at that. This is really makes a lot of things possible now that really weren't possible before. So let me just finish on this slide to say that I hope I convinced you that we are really in a new regime here where we can bridge these vast scale hierarchies through acceleration using machine learning, but in a way that's physics-based, solve previously intractable computational stats problems, connect the physics really with the data at a much finer grained level than before. And that, of course, unlocks discovery potential. I mean, one person's model misfit is another person's discovery, right? So if we find that our models aren't working, that's a good thing. It just means that there's more work to actually make sure to try to include whatever effects we're missing into the forward pipeline. And then there's a challenge in terms of model misspecification, the things that we know our models are bad at. How do we mitigate that in a way that is smarter than what's been done so far, which is typically has just been to smooth away the small scales that are complex and nonlinear. Thanks very much. Sorry for going slightly over time, but I hope that some of this can inform the discussion that's going to come next. Bye-bye.